Three, two, one.
All right. Good morning, class. We have a very special guest speaker today, Nicholas Williams. Not only is he a guest lecturer, but he's also one of our advisory board members for Wearable Tech. But more specifically, Nick Williams is one of our curriculum advisors, and he's an expert in printed electronics. He's also the director of product at XCore Therapeutics, a Baltimore-based medical device startup dedicated to improving respiratory care through the revolutionary ultra-flow carbon dioxide removal technology. XCore is a preclinical venture backed startup company, and Dr. Williams' role there is to oversee all technological research and development efforts. So without further ado, Dr. Nick Williams. Good morning, sir.
Morning. Thanks for the introduction, Henry. It's a pleasure to be here, and I see some familiar faces and some new faces. Given that this is a similar lecture, the same lecture that we gave last week, we'll try to sort of expand some sections and contract others just to make sure that we're not entirely repeating everything that we discussed last time. So we all heard Natalia gave a presentation on material science and 3D printing yesterday, and today we're going to focus on electrical engineering and nanomaterials, and specifically nanomaterials for wearable electronics. Now, I have 3 goals for this lecture that I hope that I'll be able to convey to everyone here. The first is, what exactly do electrical engineers do? Second is, how small is a nanometer? And the third is, how can we use micro and nanotechnology to advance our civilization, and specifically to improve wearable devices? And to give you a little bit of background on maybe why you should listen to me, or why potentially I hopefully know what I'm talking about. This is a brief timeline since my undergraduate career. So in undergraduate, I did research on photovoltaics or solar cells, specifically the chemistry related to that, and using that to improve the efficiency of organic solar cells. Then also developed a color change lens, also called a photochromic laminate. If you've ever seen those color changing eyeglasses that when you walk into or walk from inside to outside, the lens changes from clear to sunglasses, that's that same thing. Back when I was in undergrad, there was some new research that indicated that high energy blue and purple light was almost as carcinogenic, or was almost as cancer causing as ultraviolet light. And so what we did was we developed a color changing lens that didn't respond to UV light, which is what the current ones do, but that responded to bright white light. After that, I worked as a chemist at a battery company out in San Francisco. It's a startup venture-backed firm. I was really focusing on energy at that point. We were making huge batteries, so we were selling them on the scale of acres of land. So full city blocks were the size of our batteries. And so then during my graduate career, that's really when I started working on wearable electronics. Went to Duke in electrical engineering and focused on printed nanomaterials, specifically printed electronics. So printing circuit boards, printing various different elements to allow for the creation of low-cost electronics that are flexible, that have unique properties, and some of which we'll get into later in this talk. And following that, a postdoctoral fellow at Northwestern University in material science, doing similar things, making a wearable environmental sensor for health and safety monitoring. And now at XCore, as Henry said, the director of product. And I'm now expanding sort of just from wearable technologies for improving health to now we are making a large system about the size of a refrigerator, intended to help people breathe that have difficulty breathing. And when they sort of experience breathing failure, this will help them hopefully get better faster. But really what I'm here to talk to you today about is electrical engineering and materials, really nanomaterials for electronics. And Natalia touched on this a little bit yesterday, but I really want to get into the fact that there is oftentimes a broader experience or a broader level of distinction within a single field than there is between two different fields. So in a lot of ways, the lecture that we heard yesterday on 3D printing is more similar to what I do in electrical engineering than what I do in compared to other electrical engineers. So just to give you a brief overview of what some electrical engineers do, there's a lot of signal processing. So a colleague of mine, electrical engineer, does signal processing for the development of cochlear implants or hearing aids. They take in sound and they need to convert that sound into ones and zeros for the computer to be able to hear. And then they need to convert that into something that a patient that has hearing damage can hear. So that requires highly complex algorithms and highly complex circuit design. And so this is sort of where electrical engineers got their start, was in circuit design, and then another aspect that we'll talk about in a second. Sort of when you combine those two and move forward a little bit, now machine learning, artificial intelligence is one of the really big things that electrical engineers are focusing on now, electrical and computer engineering. And I think that we're going to see expanding interest in that. It's already pretty high, but more and more money and focus is going to go on into using machine learning and various different advanced algorithms to improve all aspects of life, all aspects of technology, from finance to healthcare to gaming to really everything. But what's needed for all of these is distributed systems. And so originally, we had one computer that was the size of a classroom. You had these large pieces of paper that had holes punched out of them in a specific pattern. You put those into a computer, and that's actually how you gave a computer commands, was with what was called punch cards. It sort of, technology advanced, and now we have cell phones that can do far more than any computer ever could back in the 1960s, let's say. But the amount of processing that we have required has gotten so intense, and the amount of data that we have has gotten so vast that we can't use a single computer for it anymore. And that's where distributed systems comes in. That's Amazon has sort of the wireless network. There are these data farms all over the country that pull large amounts of data, large amounts of energy, and it allows you to connect to them via the cloud. And so this is an active area of research on how to make it less energy intensive, how to improve it. So it's a really, really big thing that I think moving forward, we're gonna hear a lot more about. Obviously, robotics is what a lot of people think of when they think of electrical engineering. Clearly, there's a lot more to it, but the advancement in robotics really is at the core of electrical engineering. And I show this example, but the fact is, we are moving towards something similar to this. We're moving towards what's called soft robotics, where, before we see those claw machines where the robotic arm looks very robotic in a lot of ways. It looks like a machine, but there's a lot of really interesting research that allows for robots to do things that we really couldn't think of before. You can have sort of a tentacle-like shape that can grip an egg without breaking it. You can really integrate all of these new aspects into sort of modern design and things that we hadn't really conceived of 10, 20 years ago. This is really where I got my start. The PhD lab that I worked in really is a semiconductor lab. And if we think about Silicon Valley, which is now the hub of electrical and computer engineering, and in a lot of ways, a lot of aspects of technology, it all got its start from silicon, transistors, all of these. Silicon, that's an important aspect of the semiconductor industry, also important aspect of solar cells and power. But improving these transistors are of paramount importance to improving technology. To give you an example, each of our telephones has about 10 billion transistors in it. Now, these are on the scale of maybe 5 to 10, let's say 10 to 15 nanometers each. And we have billions upon billions of them within this phone, and they're doing hundreds of thousands, if not millions of calculations a day. They're switching on and off to allow for these calculations. And there is going to be a limit. We have started reaching that limit with current semiconductor technology. We can't really get down much below about 5 nanometers. We're currently at 10 to 15. We can reduce it a little bit, but we're starting to get to the point of we can't get any smaller because materials don't get any smaller. Carbon nanotubes are sort of the limit of exactly how small we can go. And below that, then we're just working with atoms. And atoms function on a wildly different scale, on a wildly different mechanism. That's where you get into quantum mechanics and things that we don't really want to have to deal with. And so that's where future computing comes in. That partially, we can think about DNA computing, we can think about quantum computing, we can think about, there's a lot of different aspects of that that we're just starting to breach, just starting to look at, but these will expand dramatically what computers can do and the speed at which they can do it. Obviously, we touched a little bit upon power, and what we're really going to focus on today is electronics hardware. But as you can see here, there's a lot of different bins in which these fit in. There are the physical components, the semiconductors, the robotics, the power. There's the programming aspects in terms of signal processing and machine learning. And there's really the sort of fundamental architecture in terms of computer design and distributed systems. And those are the 3 bins, but each of these bins covers a really broad area of interest. And there is so much more. And I wanted to take a second just to sort of show that I think with electrical engineering specifically, we really take a lot of our sort of future designs from media. So here's a quick example from, I think it's one of the early Iron Man movies, I don't really know, where, he has a touchscreen cell phone that is entirely transparent. It can wirelessly connect to various different aspects. Looks like he can log into various different computer systems with it. But what this shows is this is a goal that we wanted to reach back then. Obviously, back in, I think, 2002, 2003, this wasn't achievable. But last year, Samsung came out with what they deemed as the invisible TV. And it's a transparent piece of glass that's coated with I think it's quantum dot LEDs or maybe organic LEDs, entirely transparent when there's no electricity applied, and you apply electricity and you can come up with a TV screen that has better resolution and is transparent than the TV screen had maybe 5-10 years before that. And here's another example, and I just want to take a pause for a second, and this will just repeat, but if I could get a little bit of audience participation on this, what do you see here? You can put it in the chat, you can unmute yourself. What do you see here that is pieces of technology? So what is required to allow for this mechanical hand to be made, right? So Luke got his hand chopped off and then he got it replaced with a mechanical hand. You can see the initial functionality of it. Feel free to post in the chat, or again, unmute yourself. And I just want to take a brief moment to talk about what are the requirements for this? What needs to be invented? What needs to be used? Coding is a great example. There is a lot of computer coding and programming that is behind the ability for all of this to work. What else can we think of? Let's just take another minute or two to talk about this. Materials, there's a bunch of materials you need. One example, the skin looks like skin, right? I mean, that's obviously not his actual hand. You can see that sort of there's robotic or metal materials below that, and then there's this probably fake skin, or they grew skin in some way. That's a materials development that's needed. Other materials could be, you need to make you need to coat the metal in something that's biocompatible so that it doesn't interact with your immune system. What else? How is he able to move the fingers? So you can see, pistons working to move each of the digits. But yeah, I think nanotechnology is a great example, sort of all encompassing in this. I think the nanotechnology can be used to make it a little bit more biocompatible, can be used to enable all of these things. Some other aspects that he would need would be some connection to your brain, right? He's obviously controlling his hand with his brain. And this is a robot, so you need something to connect either your brain waves. Probably it's connected to nerves in his arm, right? I can open and close my hand just by thinking about it, and he needs to be able to do that with his arm as well. So there needs to be some connection between the brain activity and probably the nerves going down to your arm that then lead into electrical signal. Other aspects, well, I guess there are many other aspects that we could focus on, but I just wanted to take a second to show there's a lot of complexity in this. And obviously this is science fiction, and obviously this isn't reality, but we truly are moving towards this. You can see that this man lost his hand, and there's a robotic arm that's connected to a computer now, but he's able to pet a rabbit. He's able to move a duck wing without the duck experiencing any pain. So that requires sensors to be able to feel. That requires really, really fine control over the opening and closing mechanism of these fingers. And what this doesn't actually show is the three fingers that they have are dependent on nanotechnology. The sensors themselves have very fine little spikes on them, not spikes, nubs on them that allow for sensory information that's different if you touch something hard, touch something soft. If you touch something that is heavier, if you touch something that's light, all of these are required to have a functioning hand, right? You don't want to use the same strength to pick up an egg or to pick up a table. All of these things are important, and that's where the coding, that's where the materials, that's where all the nanotechnology comes in all of these different aspects. And now sort of let's talk about what is nanotechnology. It's this sort of nebulous term that's really challenging even for me, that's been working in this field for over a decade to truly wrap my mind around. And so I think the easiest way is to go up. So nanoscale all the way down there, really, really small. Let's start off with a human to a bus. A bus is, we all sort of know roughly what a city bus looks like, and we all know roughly what a human looks like. The Mount Everest is the exact amount larger than a bus as a bus is to a human. So if you scaled Mount Everest down to the size of a bus would be human-sized. If you scaled the Earth down to Mount Everest would be the size of a bus, and a bus would be the size of a human. So we're going by various different orders of magnitude. And so then the next would be a sun. The ratio and the size between the sun and the Earth is the same as the ratio and size between a bus and a human, or is between Mount Everest and a bus. And so this is 9 orders of magnitude to get from a human to the size of the sun. So that just sort of shows how large an order of magnitude is. These large jumps, takes 9 of them, but it gets us to the size of the sun. Now let's go the other direction. So human to a baseball, to a raindrop, to the thickness of human hair. That's getting close to the size at which our eyes can focus on. We can't really see something that's much below the thickness of hair. Below that is, to give a topical, COVID-19. And then finally we get to a carbon nanotube. And then just 1 order of magnitude below that is an atom. So carbon nanotubes are incredibly small. So it just shows the nanoscale is tiny. And as a matter of fact, to get to it from a carbon nanotube to a human is about 9 orders of magnitude. So carbon nanotubes are as much smaller than us as we are than the sun. And I know that we don't really know how big the sun is, or we can't really visualize how big the sun is, but that just really shows just how small we're talking about in terms of overall scale. And these are really complicated, and we've talked about all of these modern uses and all of these human-made uses for nano and micro technology, but we've really taken these from nature. Nanotechnology has been used for millions of years. Here are 3 examples of a conch shell, geckos, and a lily pad. And so if you really zoom in on those using an incredibly powerful microscope called an electron microscope. This is done with a scanning electron microscope, which shoots electrons, and you can measure the different angles that the electrons go in and get an image that looks like this. You can see that the iridescence, the sort of shiny nature of a conch shell, comes from scattering of light from these really thin sheets of calcite, I think it is, which is a mixture of calcium, carbon, and oxygen. The exact formulation doesn't really matter. They just have the ability to form these sheets that are a few atoms thick. And due to the really small nature of those and the stacking, you get that really shiny nature. And as a matter of fact, the reason why some butterflies have that same shiny nature, bird wings have that same shiny aspect called iridescence, is this. Butterflies don't actually have any pigment in their wings. It's just the different nanostructures of the wings themselves bend light in certain directions and confine light in such ways that they come up or that they create that different color and those different patterns. Geckos can run horizontally at the same speed that they can run vertically. And if you look at their fingers, if you zoom in on their fingers, you can see that it looks like there's this weird structure to it. Each finger has thousands of little hairs, and each of those hairs has thousands of split ends. And each of those split ends has thousands of split ends, and so on, down to the nanoscale. And what that does is actually so small that each of the tips of those will bind to a surface, chemically bond, and they can stick to any surface. And when they want to, so they put their foot on a surface, all of the tiny little hairs chemically bind. That sticks them on, and then when they want to walk, they just peel the finger back, breaking each of those bonds individually, and they can move their hand up. That's why they can move vertically, same speed as they can move horizontally. Lily pads have this nanostructure that doesn't allow water to actually sit on the surface. So it's really a bunch of small pillars that bundle up water on top of that so that it becomes entirely hydrophobic, or doesn't allow water to sit on the surface. And we've kind of known about this for a really long time. The Lycurgus cup is one of the first known use of nanotechnology by humans. I think it's ancient Greek glass blowers pounded down silver into very small particles, about 50 to 70 nanometers, and embedded that into glass. And you can see when light is shown on this glass from the outside, it looks green, but when light is shown on the inside, it looks red. And this is the same light source. And what happens is the silver nanoparticles absorb very specific frequencies, and they only transmit red light through. But if you reflect light off, you don't really interact with the silver nanoparticles, and it just reflects off of the glass itself, looking green. And this is what we believe to be the first example of human use of nanomaterials. But there are tons more. We already talked about. So this is different vials of gold nanoparticles at different sizes, and each of them absorb light at different frequencies. This is what's called quantum confinement. Light comes in waves at different frequencies. And if you have sizes that are about the the diameter, if you have spheres that are the diameter of that frequency, and we're talking about 50 or 400 to 800 nanometers in diameter, you can exactly capture specific frequencies of light and only transmit the light that you want. So gold, you can get it to look purple or black or red color. Red is pretty common with gold nanoparticles. We talked a little bit about carbon nanotubes. They have a lot of unique properties. They are highly electrically conductive, incredibly strong. They're about 50 times as strong as steel for sort of the same total amount. We talked about, hydrophobic surfaces and the invisible TV. You can make really interesting electronics, and hopefully that's something that we'll get to in a bit. Interesting electronics that are flexible or transparent. Cool example is liquid gold. You can have gold have this sort of nanostructure that allows for it to melt and remain liquid at room temperature. And so you can sort of have a lot of unique properties from that. And the last is a space elevator. I was actually just reading a paper recently that referred to this again, where you use these carbon nanotubes, you use nanomaterials to build a really, really long cable up into space. So you can just have this one elevator that goes into space instead of needing rockets. It'll take far less energy, far fewer resources, be far cheaper, much lower likelihood of catastrophic failure in a lot of ways. And what's required for that is materials with strength properties that macroscopic materials, just sort of steel and all of this, doesn't really have. That's where carbon nanotubes or a bunch of different nanomaterials come in. And so all of these are, sort of science fiction type uses: flexible screens, invisible TVs, space elevators. But nano and micro technology is used in a lot of things that you wouldn't be surprised with. For micro technology, carbon fiber bikes is micro technology. Carbon fibers are on the micro scale, and they make really stiff, light bike frames. All electronics, even sort of the very cheap electronics, those electronic components are on the micro scale. The printers, almost every aspect of a printer, from the ink itself, has micro and nanotechnology. The ink nozzles, the ink wells, the computer chips, the screen, all of that has microtechnology in it. Airbags use microelectronic mechanical sensors, or MEMS, to tell. It's an accelerometer, basically. It tells if your car has stopped too quickly, it'll release these airbags, and the ability to release that is based on microtechnology. Sensors based on microtechnology. Drug encapsulation, so extended release drugs, is microtechnology. You have this micron thin coating around drugs that will slowly dissolve. That's microtechnology. Those micro beads in face wash. And finally, a ballpoint pen. The actual round ball at the end of a ballpoint pen is about 100 microns. So you can see that microtechnology, it's not rare. It's not inherently expensive or reserved for sort of these luxury or future goods. It's used in everything. And nanotechnology is frankly the same. It's used in sunscreen and paint, sort of normal paint on your wall. And some of the sort of modern shirts that have, if it has anti-stain coating on it, probably using microtechnology, obviously solar cells, nanotechnology, solar cells all the way to satellites. The flame retardant or the heat-proof coating on satellites is nanotechnology. And that allows them to go incredibly fast through our atmosphere without turning to ash. All batteries do, as well as most drugs, again, have both micro and nano encapsulation. And this was the last computer to be made that didn't use nanotechnology. I think it was released in 1997. So every single computer, from your cell phone to your watch to whatever the cheapest piece of electronics you have is that has nanotechnology in it. And finally, donuts. The powder coating on donuts is nanoscale titanium nitride, safe for human consumption, but it has this really vibrant white color that for donuts people really want. And so, with that, again, nanotechnology is used anywhere from these futuristic, transparent, flexible screens all the way to food. Let's move on to talking about printed electronics. So what we can do with this, what we can do with various different nanomaterials is that allows us to make printing electronics with them. So you can see here, this is nanoparticles of silver that are suspended in this sort of viscous honey-like mixture, and you can immediately print them down. And that allows you to make, this is an antenna that's used for a wireless communication. And so this actually we're now starting to talk about the research that I have done. In my PhD, one thing that I did was make an electronic tattoo. And so you can see what I synthesized silver nanowires. So I took silver that's just in solution, liquid silver basically, and I made these really long, thin wires that are on the nanoscale. And I put those into an ink. Let's turn off the sound if we can. Put those into an ink, and I was able to print that onto my finger. And then here you can see I just took 2 ends of a battery, stuck that to the 2 different lines that I printed on my finger, glued an LED to my finger, and you can see that I can light up this LED, and I can bend my finger, I can move my finger around. So the ink is highly conductive. It is flexible. It's robust. So that allows for sort of this extended functionality. Yeah, I see a hand raised. You can feel free to unmute yourself. And
first, did it hurt to get is it like a permanent tattoo?
Yeah, no. So let's see which hand. It's this hand. So I no longer have that on there. I couldn't feel it at all. That's a great question. Couldn't feel it at all. If anything, it felt a little bit cold, because basically what it's not, I should take a step back and say it's more like a temporary tattoo than a permanent tattoo. So it just sits on top of your skin. And what it does is this silver suspended in water. I then print it onto, or I shoot it onto my skin, or I what's called aerosolize it. So I make some small droplets of them suspended in air, shoot it onto my skin, and the water dries, leaving just these lines of really thick silver nanowires behind. And what that allows is it sort of leaves these really conductive wires basically on your skin. And I just showed sort of a quick demonstration of this, printing it onto my finger, and it takes maybe 5 minutes, 10 minutes of scrubbing with soap and water to remove it. But you can wear it, you can use it for a day or two without really seeing any degradation. And just sort of as an example of how delicate it really is, you can see that I can print it onto a leaf, and I can print it in these complex shapes. So I can print, I just chose Duke and the Duke chapel as sort of a demonstration of how customizable the print is itself. And so that's one example. Let's talk about one other example, and then let's see if we can talk about or use the rest of the time for maybe a little something. so nature is actually a really great template for nanomaterials. And this is a project that I worked on a little bit recently. So if we look at plants, and specifically the cell walls of plants, they are made up of macrofibrils, which are made up of microfibrils. And so now we're already on the micro scale, which are made up of nanoscale materials that's called cellulose. And we actually know of cellulose. Everyone sort of has seen cellulose before. It's paper. That's you take wood pulp, you bash it up, you create this fibrous material that's on the nanoscale or on the micro scale. And then if you soak that in acid for a little bit, that'll start breaking the chemical bonds. There's two different regions. There's a crystalline region and an amorphous region, and it breaks down the amorphous region, leaving just this crystalline region behind. And this is the chemical structure. We don't really need to focus on that. But what that does is it allows you to take that nanoscale crystal and suspend it in water. And because you can suspend it in water, you can make an ink out of it. And that means that you can then print it. And so what we did was we were then able to print that and use that as an insulating material to protect different electronic wires. So I use this to print transistors, which again are the backbone of all electronics. And because it's plant-based, what we can do is we can actually make a recyclable, wearable piece of electronics. So what we were able to demonstrate is we printed carbon nanotube transistors, carbon nanotube electronics. You can sort of see a demonstration of printing here. I think during the talk tomorrow, Brittany is going to talk a little bit more about printing. So this is a little bit of a printing teaser. But you can then make various different types of electronic components with these, use them. And one example of a use that we demonstrated was we created a handheld sensor for measuring sweat output. It's lactate, which is if you know about sort of sports, and there's lactic acid buildup, which causes sort of that really sore feeling. You can measure that from sweat. And so you take a droplet of sweat, put it on this biosensor. You can measure sort of the how hard you're working or your health in terms of for diabetics. Frequently, they'll want to measure lactate. You can then capture all of those materials, reprint another device, and continue doing that over and over again. So this is one use of these nanomaterials is to allow for fully recyclable electronics. And so these are just sort of two examples of using nanomaterials for wildly different uses. One is specifically for you can make a wearable device. The next, you can make an environmentally friendly device. And so the rationale behind this, the reason why we wanted to focus on this, is in a ton of phones, which you think a ton of phones is a lot, but about 5 million tons of electronics are thrown out every year. It's one of the largest waste streams in the world. And about 40% of all dangerous heavy metals that are thrown out in electronics. So what we really need to focus on in the next, let's say, decade is reducing these environmentally and biologically dangerous material usage in electronics. And this is one way to do that is with these safe, these biodegradable, these recyclable nanomaterials. And I think that for the last, we have, 20 minutes left, I believe. Is that right, Henry? 20 minutes left. Let's spend 5 minutes talking about nano gold, and then I want to leave the last like 15 minutes if there are any questions. So and I'm not entirely sure we need to break out into breakout rooms this time, but let's just sort of spend a little bit of time brainstorming. So there's one situation is researchers have come up with this liquid gold. It's liquid at room temperature, and we want to find out what are some uses for it. So let's spend, I said 10 to 15 minutes, but let's spend 5 to 10 minutes talking about what are some potential uses for this liquid gold. It can be a wearable device. It can be there's a lot of different uses that we can think of. And so the properties are, it becomes solid gold at about freezing, 32 degrees Fahrenheit. It conducts electricity, it conducts heat. It can be used either inside or outside your body without any negative effects. And it has a consistency like honey. Yeah, see a hand.
Yeah, can you explain a little more how it conducts electricity?
Just like how a wire conducts electricity, where you put one voltage on one end, one voltage on the other end, and the electrons sort of move through it. That's sort of a physical object that's rigid. Liquid gold will be able to do the exact same thing, except instead of being a solid, it's a liquid. So you could put it in a glass, or you can put it onto a surface, or you can coat something with it, fill something with it.
Okay. Could it light something, like if I had enough of it, could it light up a lamp?
Absolutely.
Oh, okay.
Yeah. So what you just need to do with that is, one way that you could do is, let's say, make a mold, fill sort of one section of that mold with a pouring in liquid gold into it to fill up sort of some region, and there you go. You have a liquid gold lamp. That's certainly one usage for it. You could also probably just pour it on the outside, coat 2 different sections of the lamp, and that'll create a lamp.
Yeah. How about for my fashion students? What do you think, or how do you think you could utilize this with technology in the fashion world? You guys had some great ideas beforehand. Like, what are you guys thinking?
That's a great prompt.
All right, don't be shy. Don't be shy. In fact, Miss Elise, like how do you think, being a fashion guru, fashion tech, with Wearable, like what do you think might be a great use of this liquid gold? I think we see some things in the chat here.
So one possible, Henry, that's a great point. There's actually a lot of research going on how to use liquid metals to allow for these sort of wearable clothing integrated electronics. And so what you could do is you can take thread or string or something, soak it in the liquid gold. Liquid gold will then get sucked up into the string. And so you can have this one string that's conductive and really flexible. Right, most electronics, most wires aren't very flexible. And so if you think about, a computer cable, you obviously can't weave that into a shirt. But if you just dip a thread into liquid gold, it'll all of a sudden become electronically conductive. And then you can have electronic wires running through fabric, running through your clothes, your shoes, really anything you want. Another example that I could think of would be, again, we were talking about, for Luke's hand, you need some way to connect the neurons, or the sort of axons, the electronic conduction from your brain to this electronic hand. And that's a great way to actually do that. You take the electronic from the neuron end, use some liquid gold to be able to attach that to the actual electrical components that are guiding this hand.
All right, Karen, you got it.
I have another question.
Sure.
If can you mix silicon and gold together and still be able to conduct electricity?
Almost certainly, yeah. So, are you talking about silicon is a semiconductor, and so for the most part, unless you put a specific, unless you change its properties a little bit. So a semiconductor means that under only certain circumstances, it's going to allow for an electronic current to pass. So there's insulators, which never will, and wood is a good example of that. If you put a battery up to wood, nothing's going to happen. If you put a battery up to a metal wire, gold, silver, copper, you're going to pass that electricity and you're able to light up a light. A semiconductor, under certain circumstances, it's going to light up a light. Under most circumstances, it's not going to. And so what you can do is you can use liquid gold to as sort of connection points to help put gold into that state, or sorry, put silicon into the state in which it can conduct electricity. Yeah.
If I were to put a gold directly like outside, would it still conduct electricity?
Absolutely. Yeah.
Okay, so if I wanted to create like a silicon and gold solar panel, could I do that?
Yeah.
Okay.
Yeah, you absolutely could. And an interesting thing is that, you know, liquid gold it's going to be flexible because it's a liquid. So what you could do is you could make a flexible solar panel, right? Most of the time, solar panels are these really rigid sheets that are flat. That's really not that useful if you want to put them on a car roof, or if you want to maybe put them on something that's moving. You want to be able to have something that could be flexible, that'll also reduce its likelihood of breaking. And actually, one sort of example of flexible electronics is back when, you know, smartphones first came out, the screens would shatter all the time. If you looked at them funny, they would shatter. And we invented this thing called, I think it's Gorilla Glass or something like that, where now if you drop your phone, which if I was a braver man, I would do, but I'm not sure I will. If you drop your phone, most of the time it's going to be fine. And actually the reason behind that is there is a little bit of flexibility in the screen and all of the electronic components. There's a little give built in so that when it drops and when it has that really hard impact with the ground, it can bend just enough that it's not going to crack, but it doesn't bend too much that it breaks other components. It'll burst the battery or whatever. And so these are sort of some examples of, this isn't actually liquid gold that's used in this, but it's different nanomaterials that have allowed for that flexible screen. But liquid gold could be used as those wires in something that has to be really highly flexible.
Hey, Nick, I had a question, like going almost back to like the wearable technology. Now, if I were to infuse this, like let's say into clothes, like outside, with light hitting it, would it change the color, or would it do anything of that nature, or would we still have to be manufactured? Like, I just put some of this into my clothes and then have them, you know, look differently or feel differently, or like would it be a different process?
Yeah, I think they would feel a little bit different, just because there's going to be a little bit of this sort of nanomaterial in it. It may be a little bit less flexible, but for the most part, the exact fibers should be pretty similar, should have properties that are pretty similar. It's going to probably look gold or maybe red, depending on the size of the gold nanoparticle. So you may have sort of gold threads woven through your shirt, but for the most part, it'll look pretty similar. I mean, the currently we're using pretty thick threads just because the technology is still in development. But as this progresses, I'm sure that we're going to get down to it really just looking and feeling like normal cloth.
Great, great. Because I came up with a shoe that would incorporate light or some type of, I don't know, fibers that would change color. And so the idea of using gold, the nano gold, is amazing.
Yeah, and there's a lot of research efforts, and I think it hasn't quite gotten out to sort of the fashion industry yet, but there's a lot of research efforts to make things that will allow for that. You can weave, that you can sew, really things that are pretty simple to integrate into any form of cloth or wearable.
Wow.
Another example of nano gold, and I think we could just sort of go to these now. Here are some examples of this liquid gold that are in use today. So because it's liquid, it can form a really good connection between two different materials, and people have used those to connect electronically two different rigid materials that normally couldn't be connected very easily. And so one is for a heat sink. If when your computer, when your phone gets hot, it's because it's performing too many calculations per second, and it needs to expel some of that heat, and that's where this liquid gold can come in. Because it's a liquid, it'll conform to any shape that it's put in, and you can make really highly stretchable and highly flexible electronics. This is an example of, you can see it's a plastic or a rubber mat that they put this liquid gold into, and you can see that it's lighting up these LEDs, even when it's bulged out to 300, 400, 500 times its initial size. We talked a little bit about nerve repair, integration of these biological elements with electricity and with robotics, and this can be a really powerful use for nanomaterials and liquid nanomaterials or fluid nanomaterials. Will allow for futuristic uses and futuristic technology development. One thing that I think is really cool is self-healing electronics. So what you can have is these metal wires that have these little nano capsules of liquid metal in them. And once you cut that wire, those little capsules will break. That will then fill the void with this liquid metal that's conductive, and you can then heal that electronic. And we've now started seeing even self-healing batteries, self-healing wires. There's a lot of these self-healing electronics and self-healing materials in general, not just electronics, that are hopefully going to be on the market in the next 10, 15 years. So you can imagine if your phone screen does shatter, it'll automatically heal itself. Or you can have a watch band that has a highly flexible, highly stretchable sensor that can measure, current wearables or current watches can measure your heartbeat. They can measure your temperature sometimes. But what you want them to be able to do is to have a more directed measurement. You want to be able to have them measure for diabetes. You want to be able to just with your skin measure your insulin levels and then automatically control it. So you could integrate that into a watch band. Really easy to use, simple, it's comfortable. And then obviously there's 3D printed electronics, which we talked a little bit about, but moving forward, the printing of electronics is something that will allow for low cost uses for these in scenarios that we haven't really thought of before. And with that, we have about 5 minutes left. So I wanted to open it up to some questions. There was some good engagement thus far, but any questions broadly, and that could be, about the talk, that could be about future of wearables that could really be about anything. And so, I hope that over the past hour, I've been able to give you a little bit more knowledge on what do electrical engineers do, how small exactly is a nanometer, and what are some different uses for micro and nanotechnology, specifically focusing on wearable electronics. So thank you all, and I'd love to hear any questions.
All right, students, if you want to, you can put your questions in the chat, and then we can relay those to Nick, or you can come on the mic and ask any questions.
Yeah, I'd love to hear questions, or I can continue talking. Yeah, absolutely.
Yep. Go ahead, Karen.
I've seen this video about nano like micro robots that are put in the blood system to, if people who have cancer, it would just target the bad cells and like kill them. Have you ever seen that? Like, does it actually work?
Yeah, so to my knowledge, we do not have nano robot technology. I don't think there's anything that's small enough to be considered a robot and be on the nanoscale. And while I think it is possible that in theory you could have a really, really simple robot that could eventually do that, it will be really challenging. Now, to answer the point of, is there a nanoscale or nano-sized cancer treatment? The answer is absolutely yes. And so I talked about silver nanowires, which are just really long, thin nanowires. There are a few different nano medicines that do specifically target cancers. It turns out that the blood vessels around cancer cells, around sort of cancer clusters, are leaky. And so what that means is, if you take a nanostructured gold, nanostars, let's say, that have a bunch of different spikes around a ball that's on the nanoscale, if you inject that into the bloodstream, those will collect around those leaky blood cells. And so they'll basically just get embedded into the cancer cell. And because of that, what you can then do is then put a bunch of light on those, or a bunch of electricity, and the spikes will gather up that light and heat up the nanostar. And that will actually burn out the cancer cell. Another example is, as I sort of said before, there's nano coatings around most drugs now to allow for a timed release for extended delay. There are nano cancer treatments. I wouldn't call them robots. They don't really have any intelligence. They don't have any direct control. They just float around. They get stuck in cancer cells, and then you can use that to pinpoint the cancer and to burn it away. There's a question in the chat: is it breathable? Is which breathable?
I guess the nanofibers of a if you were to create a fabric.
Yeah, so a nano fabric or a wire that you dip in nano gold will absolutely be breathable. The breathable aspect of fibers themselves, or cloth, is the fact that they're woven together. And so you can sort of think of all cloth like this, with a bunch of different fibers that you then weave together And there's going to always be these small pores, these small spaces in between all of these fibers. So if 1 out of every 10 fibers, let's say, has gold in it, has gold sort of bonded to it, that's not going to significantly affect the breathability of that. When you think of something that isn't breathable, which is a nitrile glove that doctors use, the reason is because that doesn't have that woven structure. It's one solid piece of plastic, really rubber. But if as soon as you get that weave in there, then it becomes breathable. Good question. And so I think that's all of the time that we have for today. So I just wanted to thank everyone for sitting with me through this lecture, hopefully learning about micro nanomaterials and for their use in wearables and about electrical engineering in general. It was a pleasure to be here, and I hope everyone has a great rest of the day, rest of the hackathon, and rest of your year.
Well, before Dr. Nick leaves, can everyone begin to show your video so that we can celebrate all that was shared today?